So for this portion of Sediments Part 2, we're going to be looking at um, going from weathering products to sediments. This will lay the groundwork for sedimentary rocks, which will be done in the last section. So we sort of wrapped up the weathering, where we talked about how you get from your various rock form minerals in your igneous and other rocks, you get the following sort of residual weathering products and materials in solution. That typically your more mafic ones, in this case at the bottom of the diagram, are going to weather substantially faster and produce substantially higher amounts of minerals and residual weathering products like limonite, hematite, and clays. Now, when these all come together, if these all stay in one place, you're essentially getting a soil. Now we're going to look at what happens when these various weathering products are transported and the kinds of deposits they form. So if we revisit our sort of bones reaction series, we talked about how you're basically breaking down, you're getting three different products of weathering. Smaller pieces of rock, ions, and then what we call residual minerals. So if you and so we're going to focus on how each of these is going to have a different sort of travel history. So if you take all these weathering products, you might notice I've also rearranged them. You'll see the philosophy behind this in a moment. If you take all of these and they stay in place, what you will get, the type of sediment you'll get, will be called a soil. With your ions playing the role of supplying nutrients, your clays and residual minerals playing primarily the role of water retention, and your larger particles in your soil playing the role of maintaining permeability. However, we also know that sediment does not always, these weathering products do not always stay in place. You have major erosive forces on this planet. The Grand Canyon is essentially a testimony to erosion by water. This entire mile-deep gorge that runs hundreds of miles long is all been scoured out by water and the sediments transported to the Gulf of California. Waves also are a powerful agent of erosion. Here they are smacking into this bluff on Winden Sea Beach in lovely La Jolla. And even wind is a major agent of erosion, picking up many of those lighter particles. This is a rather spectacular example of a dust storm sweeping across somewhere, I think, Arizona. I've been to Arizona in a dust storm. It's kind of awesome. And that we see also wind erosion not only on Earth, but other planets. For example, Mars has some very dramatic, exciting examples of wind erosion. This is a dust devil on planet Mars. If you live somewhere cold or have lived somewhere cold, you probably noticed in the spring the roads are covered in potholes. This is because generally people like their roads to be plowed because it's a lot easier to drive on asphalt than it is to drive on snow. However, and then what the Department of Public Works does is then piles the snow on either side of the road. Now, if you know anything about igloos, snow is a wonderful insulator. And so what will happen is there's a little bit of geothermal heat coming out of the ground, and so that little insulation provided by snow will actually cause the base of the snow to melt. And you get water percolating into that upper layer of soil and gravel beneath the roadbed. Now, the roadbed, being first a dark color that loses energy space very rapidly when the sun is down during those long high latitude winters. and will cool off very quickly. So you take water from this that's been insulated by the snow piles, it gets under the roadway, and then the roadway is losing heat until the ice starts to freeze. Now, if you know anything about ice, when it expands when frozen. And this can exert quite a bit of mechanical rock force that will push rocks, not only roads apart, but if you have rocks with cracks in them, this is also a very effective way to fracture and fragment rocks. We see areas in polar regions and even just high latitude places that get regular cold winters where this is a major force in breaking apart rocks. And in fact, often many areas they have to actually check the cliff areas because spring is often a dangerous time because you've broken apart the rock and the ice has been the only thing holding in place. That melts and the cliff parts of the cliff will start to collapse. You don't want to be underneath the cliff when that happens. If you're in really cold places, or you also get glaciers. Where I grew up in the Pioneer Valley, we had huge regions that had been carved out by the erosive force of large masses of ice. And we also had several boulders in our backyard that had probably come from somewhere in central Quebec. And so glaciers had this sort of unique and very powerful grinding ability. And indeed, some of the highest rates of erosion observed anywhere on the planet are in places where you have steep hill slopes and glaciers, grinding up the rock and freezing and thawing, plucking the rocks apart, and other things taking place. Now, in Southern California, fire is an agent of erosion. You may wonder, wait a minute, how does fire do erosion? This is a beautiful one. So, I was talking to a guy at the Silverwood Sanctuary a couple years back. He was telling me the story of how in the Silverwood Sanctuary you have these rocks that have these very fractured granites at the surface. And the fractures will point upwards. Often there's been trees and other things also pushing apart the rock. And so you get these rocks that have these very deep running cracks that are open at the top, and water will sort of percolate its way into that crack. So when fire came rushing through, we had the Cedar Fire of 2003. Yes, this is how you draw fire. Geology is a haven. When that fire came rushing through, the this water began to boil and turn to steam. And this little crack was a little too narrow for all that steam to break out of at once. And so what starts to happen when your rock's too narrow for that steam to break out at once is that rock starts to shatter. Now, the caretaker of this bird sanctuary, told me as he was like packing his house and basically everything that he planned on taking with him for the next week or so until the fire passed through, was he could hear off in the distance the sounds of rocks exploding and shattering as the fire swept through the property. And when he came back, he saw many places that he had, this was a person who had studied basically every inch of that little piece of land. And he saw huge areas where there had been entire rock faces that had been shattered by boiling water during the fire. So this has got erosion take place, then you can move on to deposition. But first, you have to transport the water. What we're looking at here is just a little bit of transport. You can see that erosion is generally going to take place when you have a steep corner downward. Deposition takes place when you go from a steeper slope to a gentler slope, and the fluid begins to slow down. And that water, wind, gravity, and fluids will all move the various components of the sedimentary rock. And it's these different mechanisms of transport that lead to the development of different classes of sediment. For example, your smaller pieces of rock and your residual minerals are typically transported as particles in a fluid, whereas your ions are typically dissolved in your fluid. So we're just symbolizing this. We're going to have your little blue line going right through the air. dissolved in fluid. We'll see what happens to those shortly. And we're going to have our pieces of rock and stuff and residual minerals be transported in in a fluid, by a fluid. And so what you're now getting here is starting to form the basis for the major classes of rocks, so sedimentary rocks and sediments. So if your sediment is composed primarily of smaller pieces of rock and residual minerals, you're going to be known as what's called a clastic sediment. Whereas if you're primarily transporting ions, you're going to be either chemical or biochemical. Now, all sedimentary rocks, all sediments, are basically classified on two criteria. Classified on composition and texture. So composition is kind of taken care of in this column where you have your clastic, chemical, and biochemical. Your texture, you're going to see a little bit more of this in the following column. For clastic sediments, your texture is going to be defined by three different properties. The most important one is something called energy. This is a shorthand for grain size. So for example, this rock on the shoreline that was moved by the waves and water in the middle of a tropical storm, this would be a high energy deposit. Likewise, generally any fluid powerful enough to move sand also has a fair amount of energy. Now, to give you a better sense of what energy looks like here, this would be an example of low energy. These are some still waters, and you can see that the water's been still for a couple hours. This was also after a heavy rain. And you can still see there's plenty of clay suspended in the water because those very fine particles can take hours, even days, to settle out of even very shallow bodies of water. Likewise, if you go to the generally beach environment is very high energy, often if you go a little bit inland, some of those little lagoons that you find behind the beaches around here, or for example, San Diego Bay, would be classified as low energy, and you're generally going to find much finer particles. The second criteria for sediment size is rounding. Rounding. This is basically the sort of premise that moss does not cling to a rolling stone. Or in this case, as a sediment travels, the more it travels, the more round it gets. So if you were to take a rock and roll it like a bowling ball, which we'd be doing if this were an in-person class, watch the way it bounces. Try to do this in a way that it will not hit anybody. That's important. And what you'll find is that generally the rock, as it's tumbling down, will tend to strike the corners more quickly than it strikes the faces, and she'll end up with a fairly round rock the farther the rock travels. Now the final criteria is sorting. This is how consistent the consistency of energy. So we go from a very rapid current to a very slow current very quick, abruptly. A lot of particles transported in that current are all going to fall out in about the same place. A good example of this would be a flash flood. In the case of one of these events, you're going to have a poorly sorted deposit. Whereas if you have a very consistent current, you'll get a very well-sorted deposit where most of the particles will be just about the same size. So now we've covered the major textures, we'll now focus on the rocks in our next part of lecture. Thank you very much.